Welcome to Multi-Electro.
Welcome back to the channel. In today's video, I'm going to show you how to build a powerful electricity generator using a car alternator with a custom rotor made from 12 neodymium magnets. And we'll also test it with an electromagnetic rotor. First of all, we'll test it without the magnets. For this, we'll take 4 diodes and connect them together just like I've shown in the video. First, we'll take 2 diodes and connect their positive ends together. After that, we'll take the other 2 diodes and connect their negative ends together. Now we'll connect one negative end and one positive end together. One negative end and one positive end together. The 2 positive ends that we connected together, and the 2 negative ends we joined together. We'll connect both of them to the rotor's carbon brushes. And the negative and positive ends that we connected together. One of them will connect to the winding wire. The other one will connect to one terminal of a 10 UF capacitor. And the second terminal of the capacitor will also go to the winding. Now we'll connect the voltmeter to the winding wires. And then we'll spin it and check the output. When we spin it using a rope, it's producing around 100 volts of output. Now we'll connect a light bulb, and spin it again to check the result. Now we're going to open the alternator so we can install the magnets inside. First, we'll carefully remove the outer casing and separate the front and back housing. Make sure to loosen all the bolts properly and keep the screws safe so nothing gets lost. After that, we'll take out the rotor assembly and inspect the internal parts. We need to create proper space for the 12 neodymium magnets on the rotor. Everything must be aligned correctly and securely fixed to avoid imbalance while spinning. Proper positioning is very important for maximum magnetic performance and smooth operation. Now we'll take 6 neodymium magnets and place them on one side of the rotor. We'll position them with the positive side facing upward. It's very important to keep the polarity consistent while placing each magnet. Make sure they are evenly spaced around the rotor to maintain proper balance during rotation. We'll carefully fix them in place using strong adhesive so they don't move while spinning at high speed. Proper alignment is critical because even a small imbalance can cause vibration. Once all 6 magnets are securely attached, we'll let the adhesive dry completely before moving to the next step. Now we'll move to the other side of the rotor and fix the remaining 6 magnets. This time we'll place them with the negative side facing upward. The polarity must be opposite to the first side to create a proper magnetic field interaction. Just like before, we'll carefully align each magnet evenly around the rotor to keep the balance perfect. We'll use strong adhesive to secure them firmly in place. making sure they don't shift during high-speed rotation. Proper positioning and opposite polarity are very important for maximum efficiency and smooth generator performance. Now we'll carefully reassemble the alternator. First, we'll place the rotor back into its original position inside the housing. Then we'll align the front and back covers properly. Making sure everything fits smoothly without touching the magnets. After that, we'll tighten all the bolts securely. Now the alternator is fully assembled and ready for testing. Now we'll connect the voltmeter to the output terminals of the alternator to measure the voltage properly. Make sure the connections are tight and secure before starting the test. Once everything is set, we'll use a rope to spin the alternator manually. As the rotor begins to rotate, the magnets will create a magnetic field inside the stator winding. Keep an eye on the voltmeter while spinning to observe the voltage increase. This will help us understand how much power the modified alternator is generating. The faster we spin it, the higher the voltage output we should see on the meter. When we spin it using a rope, the alternator is now producing around 18 volts of output. As you can see on the voltmeter, the reading stays stable while rotating. This shows that the magnetic setup is working and generating a consistent voltage under manual spinning. Now we'll fix a pulley onto the alternator shaft so we can spin it more efficiently. Make sure the pulley is properly aligned and tightly secured to avoid slipping during high-speed rotation. Once the pulley is installed, we'll connect it to a grinder using a belt. The grinder will help us achieve much higher RPM compared to spinning it with a rope. After setting everything in place, we'll carefully power on the grinder and let it rotate the alternator. While it's spinning, we'll monitor the voltmeter closely to check the voltage output and see how the generator performs at higher speed. When we spin the alternator using the grinder, the speed increases significantly compared to manual rotation. As the RPM goes higher, the magnetic field cuts through the stator windings much faster. Because of this, the voltage output rises quickly. On the voltmeter, we can see that it's producing close to 100 volts. The reading remains strong and stable while the grinder maintains consistent speed. This clearly shows how important rotation speed is for power generation. Higher RPM directly results in higher voltage output, proving that our magnetic rotor setup is working efficiently under high-speed conditions. Now we'll connect a 100-watt light bulb to the alternator and test it under load. Once the bulb is connected, we'll spin the system again using the grinder. As soon as the bulb turns on, it starts drawing power from the generator. You'll notice that the voltage reading on the meter drops compared to the no-load condition. This happens because the load demands current, which causes the voltage to decrease. Even though the voltage reduces, the bulb lights up clearly, showing that the generator is supplying real usable power under load conditions. Now we'll set up the system to supply current to the electromagnetic rotor using diodes. We'll install the diodes properly to control and direct the current flow to the rotor winding. This will allow the electromagnet to create its own magnetic field when powered. After completing the connections, we'll spin the alternator again and carefully monitor the voltage and performance. Then we'll compare the electromagnetic setup with the permanent neodymium magnet system. And now we'll test the electromagnetic system. We'll supply current to the rotor winding so it can generate its own magnetic field. Then we'll spin the alternator and carefully observe the voltage output and performance under load. This will help us compare it directly with the permanent magnet setup and see which system works better. As we've seen from our testing, the electromagnetic system performs better than the permanent magnetic setup. The voltage control is more stable, and the output under load is more consistent. With the electromagnetic rotor, we can adjust the field current to regulate the power more effectively. You may have noticed that almost every commercial generator uses an electromagnetic system instead of permanent magnets. That's because electromagnetic rotors provide better control, higher efficiency, and improved performance at different speeds. This is why modern generators rely on electromagnets for reliable and adjustable electricity production in real-world applications.
Thanks for watching. See you in the next video.